Hello. Today we will have a bit of a lesson which is ahead of our schedule. We want to go over the concept of computing the eigenvalues and eigenvectors for 2 by 2 matrices. We will cover the topic of eigenvalues and vectors in more details after we go over the general concept of linear transformations. But because the students in my class that are taking right now the course on differential equations might need these a little bit earlier, I thought I should go over this concept a little bit earlier and just focusing on the computational aspect for 2 by 2 matrices. So hopefully it's not going to be too much of a disruption in the logical flow. So before we get, and again, the whole lesson will be just focused on the computational aspect, but just briefly, this concept of eigenvalues and vectors, like I said, it will appear in different contexts. In the case of differential equations, you'll see this immediately popping up when trying to solve or when designing a formula for solving or a method for solving a linear homogeneous system of differential equations. So in the 2 by 2 case, something that looks like this. Let's say x and y are the dependent variables, right, depending on t, and then let's say the right hand side is a linear combination in x and y, and a, b, c, d are constants. So those of you who take differential equations course, you will learn that actually the solution is going to boil down to analyzing this matrix of the coefficients of the system and finding its eigenvalues and vectors for that matrix. In the context of linear transformation, so let's actually write a quick intuitive definition here. A linear transformation, basically, it's a function, basically, that is a function that defined on vectors. A linear transformation is a function that assigns a vector to another vector. And this is done for various purposes. Geometrically, if you think about vectors represented by arrows, you can design or you can define linear transformations that do some geometric transformations like rotation, translations, and so on. So the eigenvalues and vectors are related to linear transformations, first of all, defined by a matrix. So any n by n matrix defines a linear transformation. And it is easy to see that because no matter which matrix you pick, so let's, as an example, let's say you have a matrix A given by the components 1, 1, and 4, 1. So if I multiply this matrix to any vector, and in this case we're going to take the vectors u, v, and so on from R2. So to be more precise, any matrix defines a linear transformations on Rn, right, on the vector space of column matrices. So if I multiply a matrix with this matrix with a vector, then of course I'm going to end up with another vector, another column matrix, right? So to illustrate, if you take a typical column vector with two components, let's say A and B, right? This will be the input. In this transformation, the output, of course, is given by the column matrix coming up from this multiplication. So this will be the output of the transformation. So given a transformation represented by a matrix, another question you can address, which is again related to the eigenvalues and vectors, which vectors change their magnitude via this transformation. In other words, magnitude is represented by changing the scalar coefficient. In other words, if I take a transformation given by a matrix, I can ask the following question: what are the set of vectors that under this transformation only change their magnitude, meaning that A times V is just some scalar multiple times V. So I call this scalar multiple lambda, just because it's a traditional notation for the eigenvalues. So basically the set of scalars lambda and the set of vectors V that satisfies this equality are called eigenvalues and correspondingly eigenvectors. All right, so we want to find the set of lambda and V's specific to the matrix A that satisfy this equation. Right, so we could have started with this and use it as a definition, but I thought it's just to justify it a little bit in the context of applications to differential equations. By the way, for linear systems in the context of differential equations, these eigenvalues and vectors will come up from looking at exponential solutions. So if you look at the exponential type of solutions for that system, that process lends itself to this type of equation that gives you this eigenvalues and vectors. Okay, so let's write down a couple of remarks. The first important remark is that obviously we're looking for non-zero vectors, because that's the trivial case, right? The whole point is to modify the magnitude. We're not talking about magnitude 0. Obviously, A times 0 equals 0. So we're looking for non-zero vectors. And that has an implication. And as it turns out, actually, this remark here, it's the reason is the one that gives you a way to find lambda, the eigenvalue. So let's illustrate what this equation becomes in the 2 by 2 case. In general, if I have a matrix A, B, C, D, and I multiply it by a vector with components V1 and V2, if I want that multiplication to be lambda V1 and V2, then if I come up with the whole computation on the left and on the right, we get to a system in V1 and V2. AV1 plus BV2 equals lambda V1. CV1 plus DV2 equals lambda V2. All right, and let's simplify this. Let's move everything to the left side, so I can see exactly what the coefficients are of this system in V1 and V2. So notice that I can pull V1 on the left, and the coefficient is A minus lambda. And the same thing on the right hand side, I can pull out V2, and I get D minus lambda V2. So the system that gives me the eigenvector is a homogeneous linear system in V1 and V2. Written in terms of a matrix format, the matrix of this system, again, don't confuse this matrix with the original matrix, right? Coming from the original setup here, right? So the matrix of the system that gives you the vector V1 and V2 is obtained from the original matrix and subtracting lambda from the main diagonal. We can formally write this system as A minus lambda I, where I is the identity matrix, multiplied by some vector V equals to the... Alright, so sorry for the cutoff. The system stopped working all of a sudden, so I had to restart the slide. So we were talking about the fact that the system that gives me the eigenvector can be written in the matrix form like this. Now remember, our original matrix was A, B, C, D, right? And then the system that gives me the eigenvector is actually, in terms of a matrix of coefficients, obtained from the original matrix A, but with lambdas subtracting from the main diagonal. You can, in a more compact way, indicate this fact, this subtraction from the main diagonal, as the difference between A minus lambda times the identity matrix, right? So it's like you have A, B, C, D, minus lambda scalar multiple with 1, 0, 0, 1, right? So minus lambda I, it's a compact way where I is the identity, right? The identity matrix. It's a compact way of stating that you subtract lambda from the main diagonal. All right, so let's remember our important remark that we're looking for non-zero vectors, right? Right, these vectors in terms of v1 and v2. So remember the connection between the nature of solutions of a system of equations and determinants. If you look at your system here in the matrix form, remember if the determinant of this matrix happens to be not equal to 0, then it will have a unique solution. That is one of the main properties of properties of the determinants. So the system represented by that matrix, it will have a unique solution provided the determinant is not equal to 0. Now, this is what exactly we do not want. Why? Because that unique solution will be the 0 solution. Since it's a homogeneous system, there's 0 on the right hand side, the trivial, the 0, 0 solution is always there, right? It will always have a 0 solution. So if you have a unique solution, then it must be just the 0 solution, which is not what you're looking for. So that is the key thing, right? And because we look for the eigenvector to not be the 0 vector, then we must have infinitely many solutions. Because that's the alternative in this case, right? I mean, if it's not a unique solution, the determinant is equal to 0. So that's going to happen if the determinant of the matrix A minus lambda B C D minus lambda is actually equal to 0. So this is the so-called characteristic equation that you get to solve for lambda. It's the characteristic equation that gives you actually the value or the values, as the case may be, of the eigenvalue of lambda. So to summarize, we can write this as a compact recipe. So to find lambda and v such that AV equals lambda v, right? So the eigenvalue is an eigenvector. You proceed in the following way. The first thing, you're going to set up the determinant of A minus lambda I equal to 0 and solve it for lambda. And you can have various situations, you know, the real roots or complex roots. In this class, we're going to deal with the real roots primarily. If we have time, I'm going to show you the version with the complex roots, but you know, the overall procedure is similar. So that gives you the eigenvalue. And then for each lambda, in the second step, for each lambda found on the previous step, find the vector v bar such that A minus lambda I v bar equals 0 bar. So you solve then for each lambda, you solve the system in v1 and v2 for each lambda. Okay, so let's illustrate this with an example. And by the way, you should expect infinitely many solutions. Usually we give a representative of these solutions. I think this cut off one more time. Let me pause it for a second. Right, so I had another accident before when the software cut me off all of a sudden. Hopefully it's not going to happen again. So let's do our first example. we start with the matrix. I just wrote it, but let's write it one more time. So take the matrix 1, 1, 4, 1, the one that I wrote previously, and let's follow the procedure for finding its eigenvalues and vectors. So like I said before, the first step is to set up the determinant, the so-called characteristic equation, right? So you subtract lambda from the main diagonal and form a determinant set equal to 0 and solve for lambda. All right, so that means in this case that's 1 minus lambda squared minus 4 times 1 equals 0. Let's square that, parenthesis, and that gives me lambda squared minus 2 lambda minus 3. So it will be a quadratic equation in the case of a 2 by 2 matrix. Oh, it's always the case. And then solve it, right? So in this case we can factor it between lambda minus 3 and lambda plus 1, which means we have two eigenvalues, and count them like lambda 1, lambda 2. So lambda 1 will be minus 1 and lambda 2 will be 3. So two eigenvalues in this particular case. Okay, so now for each eigenvalue, so starting with lambda 1 equals minus 1, form the system that gives you the eigenvector. So go back to the matrix where we subtracted lambda from the main diagonal and subtract the eigenvalue you just found, and form a linear system which is with 0 on the right hand side, a homogeneous linear system. For larger matrices, this is the moment when you could do the row reduction and things like that, right? The row operations to find the reduced row echelon form. So the reason I actually go over this case 2 by 2 separately is because I want you to do it much faster. No reduced row echelon form needed. These are smaller systems, when you have two equations and two unknowns. And in particular in this case, because remember the determinant of this determinant is equal to 0. So the determinant of this system is equal to 0. And you know that means the rows are dependent. Since there are only two rows, it is always the case that one row is a scalar multiple of the other row. So that means you basically can ignore one equation and solve for the other. Technically, if you go by the reduced row echelon form, I mean, you will divide the first row by 2, and then you subtract, you can multiply the first row by -2 and add. So basically, in this 2 by 2 case, you always end up with a single pivot. And you basically solve for V1 in terms of V2, right? So V1 plus V2 over 2 will be 0, and V2 will be arbitrary. But from a practical standpoint, you basically solve one in terms of the other, and that other is just an arbitrary parameter. So you don't have to go with this whole formality of the reduced row echelon form. Just pick one of the two equations. So I'm going to pick, for example, the first equation. Declare one of them to be an arbitrary, to have an arbitrary value, and solve for the other. And at all, if it's possible, try to avoid fractions so that your eigenvector is as nice as possible. All right. So, for example, in this case, I'm going to just basically declare V1 as arbitrary. So let's call it R, or give it some other symbol. And then I'm going to solve for V2. So therefore, a typical eigenvector corresponding to this particular eigenvalue will be in the form R minus 2R. If you look carefully, it's just going to be a scalar multiple of 1 minus 2. So it's customary to pull that scalar multiple and choose as one representative of the eigenvectors, because again, for each eigenvalue you have what's called an eigenspace, right? It's not just a single eigenvector, it's an eigenspace. It's actually a vector subspace of the original of R2, of the original vector space. And then you're providing the basis of the eigenspace, which is essentially what comes out after you write this in terms of a linear combination. So to summarize, corresponding to lambda 1 equals -1, you're going to have the eigenvector 1 minus 2, or any scalar multiple of it will do. Always write them together, because when you get to use these in, when you get to use this for solving linear systems of differential equations, then you have to basically pick, in the solution to associate the eigenvalue with the corresponding eigenvector in that part of the solution. Now, you do the same now for each eigenvalue, right? So let's move on to the next one, lambda 2 equals 3. Subtract it from the main diagonal of the original matrix. 1, -3, 1, 4, 1, minus 3. And now the equations, the matrix of the system is 2, -2, 1, 4, -2. Notice again that one row is a multiple of the other. No, don't bother with the reduced row echelon form. Simply take the easiest equation. The easiest thing is to again solve in terms of V2, because that avoids fractions. Take V1 to be arbitrary. And then solve for V2. So V2 is going to be 2R. R to R is the eigenvector, and I can pull R. And then my eigenvector will be 1, 2. You can just write 1, 2 directly. So what I actually encourage you to do in the 2x2 case, starting from here, basically plug in a convenient value for V1 or V2 and solve for the other. And any combination will do. The obvious choice is usually 1. Usually the choice is 1. Not always, but usually, in order to avoid fractions. Not because fractions are forbidden. It just leads to easier computation if you avoid them. We will do 2 more examples on the next page, and I think that's enough for the 2x2 case. All right, so let's take another matrix. Let's say A is equal to 1, 3, 3, 1. One thing I want you to notice, let's actually do the steps like before. 1 minus lambda 3, 3, 1 minus lambda equals 0. The characteristic equation is 1 minus lambda squared minus 9. That gives me 1 minus 2 lambda plus lambda squared minus 9 equals 0. Which is lambda squared minus 2 lambda minus 8. You can use the quadratic formula. Let's actually use the quadratic formula, although it factors nicely. 2 plus minus negative 2, right? 2 plus minus -2 squared minus 4, 1 minus 8 over 2. That's 32 plus 4, which is 36. So we have 2 possible eigenvalues. 2 minus 6 over 2, that's minus 4 over 2, which is -2. And the second one is 8 over 2, which is 4. All right, and then now again, just like before, starting with -2, subtract. As a double check, always check to see if the rows are dependent, like if one is a scalar multiple of the other. Right, in this case it's pretty easy to see because the matrix of the system is just 3, 3, 3, 3, right? So obviously they are identical, but remember, in general you need to have one multiple of the other. So you can pause a little bit and follow the computation, because I do it a little bit faster, but just pause the video if you want to catch up. But once you get the hang of it, it's pretty easy in the 2x2 case. Once again, you pick any equation. In this case, doesn't matter. You can divide by 3 both sides. give it a non-zero constant, non-zero value for one of the two, and solve for the other. So for example, I can assign 1 to v1, and then of course v2 is -1, or I could do 1 for v2 and then v1 is -2. Again, any scalar multiple of this will be as good as any, right? So in the formula for the solution of differential equations, you need to take an eigenvector. Either of these will do. Most people obviously will choose as small numbers as possible, right? So I will choose 1 and -1 or -1, 1 for the eigenvector. And then similarly, for the second eigenvalue, 4, subtracting from the main diagonal, 1 minus 4, 3, 3, 1 minus 4. Sometimes I don't even bother to set up v1 and v2, because again, in the 2 by 2 case, it's so direct. But in the beginning, just go a little bit more formally till you get used to it, right? So again, in this case, it doesn't really matter which equation I pick. They're pretty similar. Let's say -3v1 plus 3v2. I can divide by 3 and see if you can extract the eigenvector. You can pause the video now and just give me the eigenvector, or write down the eigenvector. That is the easiest one to come up with. So hopefully you just did that, and you notice that since v1 is equal to v2, then I can just use 1, 1 for the eigenvector as a representative of the eigenvector. So again, if you were to be picky with the language, when someone says, give me the eigenvector for a given eigenvalue, you really mean for this particular eigenvalue, give me a representative of the eigenspace, or a basis of the eigenspace. Now, again, I'm getting a little bit ahead of myself in this class because we didn't talk about bases yet. But I mean, out of infinitely many, just pick one in this case if you write it as a linear combination, right? In this case, it's just a scalar multiple. But we'll talk about eigenvectors and spaces more formally once we go through the linear transformation part of it. One last remark before I move on related to 2 by 2 matrices, which I think is useful to keep in mind. When you look at this characteristic equation, right, coming up again from the original matrix A, B, C, and D, when you set your characteristic equation, which is the determinant of that matrix, if you write down these computation and you rearrange the terms starting with lambda squared, if you look carefully at the coefficients of the characteristic equation, they are related to two typical quantities related to the original matrix. You have a minus in front of the parentheses in the middle, and in the parentheses you have the sum of the main diagonal of the original matrix. That's called the trace of the original matrix. The trace of A is the sum of the elements of the main diagonal. The constant, the term independent of lambda happens to be the determinant of A. So actually you can go direct from a matrix to the characteristic equation by simply writing lambda square minus the trace of the matrix times lambda plus the determinant of that matrix. This is only in the 2 by 2 case that holds this. So I would go just quickly to this quadratic if you remember this fact. So for example, if I look back on the top corner here, so my matrix is 1, 3, 3, 1. Then the equation for the eigenvalue that gives me lambda is simply lambda squared minus the trace, which is 1 plus 1 in this case, plus times lambda plus the determinant, which is 1 times 1 minus 3 times 3. So you can just go straight to the quadratic lambda square minus 2 lambda minus 8 equals 0. So you can kind of bypass this entire computation here in the top row. That's not overly important just for the sake of finding lambda, but you know, for example, when you study the stability of equilibrium in the 2x2 case, again in the context of differential equations, then you can characterize easily the some equilibrium points in terms of the signs of the trace and determinant. So that's all for today, and we'll continue with linear transformation next time.